Hi, everybody. Trying to get rid of some options. There we go. Um, this screencast is just sort of a companion piece to reading the textbook, chapter 14. So I'm not going to work straight off of the textbook, although it is certainly something that you'll work from. I don't seem to have it open right now, but I guess I'll open it here for reference if I can handle Google Chrome. There we go. So we're in functional programming for R, and section 14.3, purrr higher ordered functions. And we'll do about half of it in this screencast and the second half in the other screencast, and just see how it goes as see whether this is a useful resource for you in practicing how you would read this textbook and pick apart the code, study the code that is in it. So rather than work directly from the text, I'm going to be working, just to speed things up, with the R Markdown source file for the book that I've written. But of course, you'll be doing a lot of copying and pasting the code. And I don't know if you've noticed this, but you can copy a code chunk by heading to the corner, and that gets it straight into your clipboard. You don't have to be like athletic and figure out like how to capture it all with your mouse. You can just copy it right here. Wahoo. So I'm going to head to RStudio with the source file, and to get us started off, we're going to need tidyverse, that back from chapter 10, and we'll also need beginning computer science with R, because it's got some data sets that we'd like. Alrighty, let me head down to the section 14.3, purrr higher ordered functions. Alrighty. And say we have this the following task. We want to generate 5 vectors, and each vector is going to consist of 10 numbers that are randomly chosen between 0 and 1. You could do this with a loop. You could say, well, I'm going to have 5 vectors. I'm going to pack them into a list. And so you might say list is vector, mode equals list, length is 5. So that's a way of creating a sort of an empty placeholder list of any length that you like. So there's LST in our global environment over here. And then we could bust out a for loop. For I in 1 to 5, list in the ith place is 10 random real numbers between 0 and 1. So let's run that for loop. And then list is going to have some stuff in it. Notice that, by the way, I gets into our global environment with the last of the values in the iterable 1:5. Anyway, checking out list over here, sure enough, 5 items, each of which is a numerical vector of length 10 full of these random numbers. That's all very well and fine. What if we wanted the list to have vectors of different lengths? Okay, so what if we wanted the first vector to be of length 1, the next to be of length 4, the next to be of length 9, the next of 16, and then the final one of length 25? Could you vary the code to get that done? Well, just noticing that 1, 4, 9, 16, and 25 happen to be the squares of the numbers from 1 to 5, you could write a for loop that takes into account. Here, let me grab list again. It's now an empty list of length 5. And in the for loop, the ith place of list shall be set to I squared number of random real numbers between 0 and 1. So let's run that. And pow, it worked. The first vector is indeed of just length 1. The second is of length 4, the third of length 9, and so on. Very nice. Now, there doesn't really have to be any particular pattern in the lengths of the vectors that you want. For example, in this situation here, we'd like a list of 5 vectors where the lengths are 5, 7, 8, 2, and 9. I don't see any real pattern in those numbers. So what I'm going to do is just stick them into a vector called vec. There it is in our global environment. And we'll make that empty list again, but it's going to be of length vec. And that way I don't have to keep track of how long vec is, but it's still 5 units long this time. And then I go for I in 1 sec-along vec. That's just a sophistication. You could say 1 to the length of vec, but it's a little safer to do sec-along vec, and I'll demonstrate that by just running this little section right here, this little selection. Run the selected lines. And whoops, that didn't work. I wanted to run just that little selection, so I'm just going to copy it, take it down to my console, and run it. And you see that it turns into the 1:5. So now we say that the list in the ith place shall be r UNIF of the ith place of vec, and so that will give us ith place of vec number of vectors to go into this list at that stage in the for loop. Let's run that for loop, and we get the desired results over here in the global environment. So my question to you is this. In this for loop, you're just applying r UNIF to every element of that vector vec, one at a time. Is there a way that you could apply an arbitrary function to each element? Not just r UNIF, but any function that you want to apply. Well, certainly you could just change the code for the for loop, and instead of having the r UNIF call in the line 278 here, you could have, another function that deals with vec I. But there is a cool way to handle it all without for loops. And it's by using the map function that's in the purrr package. Now, the general form of the map function is that it has 2 initial parameters that have funny names. The first parameter is called .x. And it can be any list or any atomic vector. This basically is like an iterable, something that be gone through one by one. And the second parameter is going to be set equal to a function that's going to be applied to each element of that iterable x. And so what the map function is going to do is mimic the behavior of a for loop without you having to set up all the syntax for the for loop with all of those, curly braces to mark off bodies and these things in parentheses to, set up your index and iterator. It's all going to be done through a function called map. Now, there's other arguments that can come after it, and we'll learn what those arguments can be in a bit. Now, the result of map is always going to be a list of some sort, like the ones we've been producing. So how might we use map to get the results of the last for loop that we worked with? Well, I'm again going to set up a vector of the desired length of the vectors that will be in my final list of random numbers. And I call it how many. And then I'm going to bind the name LST to the result of the following chain of functions. I start with how many, and I pipe that in as the first argument to the map function. So the how many is going to be the .x argument. And the .f argument is set to our UNIF. So let's go ahead and I'm going to clear my global environment so you can see very clearly. And get how many in there. And now we'll get LST. LST is a list of 5 things, and check it out. They're the vectors of random numbers, each of which has the desired length. Now, all of the numbers that are generated inside these vectors, they're all random numbers between 0 and 1. That was the default value for the min and the max parameters of the RUnif function. But if you wanted to supply different mins and maxes, you could do that through that ... extra arguments in the map function. So check out this next example. Here, we start with how many, pipe it in to be the first argument of map. Second argument is still RUnif. We got 2 additional arguments. Min is 4, max is 8. And what map understands is that those are arguments that are to be applied to the RUnif function when it's called up to work on each of the elements of how many. So let's give this a try. So sure enough, our 5 resulting vectors have the desired lengths. But you'll notice now that they're no longer random numbers between 0 and 1. It looks like they're random between 4 and 8. So this is the key idea about how map works. It says, hey, I've got this how many vector, and I'm going to be fed one of its elements at a time. And each time I'm fed one of its elements, I call up RUnif and stick the element that I'm fed in as the first argument. The other things would be set up as other arguments to RUnif. Because the how many element is set up as the first argument, and RUnif works by its first argument is how many random numbers you want, that's why these vectors end up having those desired lengths. So this is kind of cool. There's all kinds of stuff that you could then ask for here. So like what's happening here in this code chunk? I'm going to clear the global environment again. And we're going to set lower bounds to be the numbers 1, 2, 3. And then we're just going to print out to the console lower bounds piped in as the first argument to map. And so what happens is each element of lower bounds is going to become in turn the first argument of RUnif. So I'm going to generate 1 random number, then 2, then 3. At least that's your thinking about how it's going to work. But when map actually gets running, it looks at its extra arguments. And it says, ooh, n is 2. Well. N is the name of the first parameter in RUnif. It's how many random numbers you actually want. And that's getting set here. And so map says, oh, wait a minute. The elements of lower bounds are not going to be like how many random numbers I want each time. They must be something else to do with our UNIF. And it checks out and sees that the next thing it's provided for is the max is 8, and it thinks, you know what? The min wasn't provided. Lower bounds must be the min. So I'm going to generate 2 random numbers each time, but what's going to be changing on me, says Map, is the lower bound for what I'm generating. Let's give this a try. So we run this code chunk, and sure enough, it's a list of 3 vectors, each of which is of length 2. But the first time the lower bound was a 1, the second time it was a 3, and the second time it was a 2, the third time it was a 3. Each time the upper bound was an 8. Now, in all the examples that we've done so far, we've had one parameter that's changing on the map function each time. And it uses positions of parameters in the .f function to figure out what it is that's changing on it. But you can actually get more than one thing to change on map at a time if you put the things that you want to change into vectors and make a list out of them. So like say you want to change how many random numbers you're generating each pass through. You want 3, then you want 1, then you want 4. Make that how many. And let's say you want the upper bounds to change. The upper bound should be 1, then 5, and then 10. So you set a little vector called upper bounds. And then we're going to put those 2 vectors together to make a list. And we're going to pipe that list into a cousin of map called Pmap. P stands for Polylocks. You're going to change more than one thing at a time. And the .f is still our UNIF, and the extra argument is min is 0. And so let's see what happens. So sure enough, you get a list of three things: vector of length 3, vector of length 1, vector of length 4. The min was 0 each time. Now, what was not specified here after our UNIF is the number and the max. The number n comes before the max in the definition of our UNIF. And so Pmap looks and says, this how many thing that was the first thing in the list I was given must correspond to the number of vectors that I'm supposed to produce. And this upper bounds thing I'm given must correspond to the max, since that was not mentioned after the RUNIF. So that's how the Pmap does its work. Again, it's using position as well, just like map does. So really, if you wanted, you could vary all 3 things at once, like in this code chunk. So you can vary how many vectors you want to produce each pass through, what their lower bounds shall be, and what the upper bounds for the numbers shall be. So I'm just going to go ahead and put all 3 of those vectors into a list, call it args. And I'm going to pass args into Pmap RUNIF. I don't bother to put any extra arguments into my Pmap call because the how many is going to be interpreted as the n, the lower bounds will be interpreted as the mins, and the upper bounds will be interpreted as the max. Let's see how it works. Yep, sure enough, the structure shows us that we got a list with a 3-element vector, a 1-element vector, and a 4-element vector, lower and upper bounds as specified. Now, so far in the examples of map and pmap that we have been working with, the .f parameter has been set to our UNIF. Now, you could set it to any function that R knows about. You could set it to a function that's already been defined for you in base R or in some package. Or you could actually define that function yourself and throw it in as the argument to the .f. So look what's happening here in this code chunk. So I'm defining a function that I'm going to call R letters. It's a function of two parameters, in and upper. And upper looks like it's supposed to be a logical true or false because I've got an if statement here. If upper, then I'm going to sample from capital letters, size is in that was provided by the user, replace as true. So that means I'm taking in letters with replacement from the capital letters. But if the upper is false, I'm going to hit inside this body of the else clause, and I'll be sampling from the lowercase letters. Okay. So let me go ahead and just teach this function to the global to the global environment. I'll clear out the global environment first to make things more clear. And let me just give it a little whirl here. So I'm going to copy that function, go down to the console, whoops, and copy it. Teach it to the global environment. And I'm actually just going to try it out here. R letters, where I say that the in shall be 10 and upper shall be false. And sure enough, I get 10 randomly picked lowercase letters. Okay, so I've got this function. And the next thing I'm going to do is set up a little vector in that is 369. And I'm setting up a little vector called upper that's true, false, true. And then I'm going to put those two vectors together to a list, and then I'm going to feed them to Pmap, where since it's fed into Pmap, this list is the .x argument. The .f argument is my R letters that I've defined. So I predict that what Pmap is going to do is it's going to say, my R letters needs two variables. It needs the in and it needs two arguments. It needs the one for the in and the one for the upper. This first thing in my list must be the stuff for the in, and the second thing in the list must be the stuff for the upper. So let's see if this is working out. And whoops, I need to just run the whole code chunk here. And there we go. And sure enough, upper was true, false, true, so I should have uppers for the first and the third and lowers for the middle one. Yes, I do. And look at the links. They work out. 3, 6, and 9. Now, I want to be careful that you understand that the names for these two vectors that made up that list are not important. I could have called this first one George and this second one Bettina. And then when I make the list, I make it out of those two vectors, George and Bettina. And it should still work. Let me run the code chunk again. Yeah, it still does the same thing. The parameters for the function RMap are named in and upper. The arguments that are provided for those parameters can be named whatever you like. Now, in our last example, we wrote that function, R letters, defined it ourselves. We bound the name R letters to that function in our global environment, and then we brought up Pmap. But it's totally okay to call up a map or a Pmap and to give it the .f function written right there on the spot without a name attached to it. So check out this code chunk. I'm going to run it first. Then I'm going to explain like why it is how it is. So .135 is going to come in as the .x argument to map. This next expression must therefore be the .f argument. And it's a function of some element x. What you do is you take 3 random numbers where the min is 0 and the max is that x. And so what's going to happen is that map is going to run that function first where x is 1, then when x is 3, and then when x is 5. So in this first vector, the upper bound was 1. In this next vector, the upper bound was 3, and in this next vector, the upper bound was 5, although by chance the numbers came out a lot less than 5. If I ran it again, and again, and again, you'll see that sometimes we do indeed get random numbers that are close to that upper bound that changes each time through. So a function like that, that's set up but not named anywhere, is called an anonymous function. That's a common concept in computer programming. Because it's such a common thing to define anonymous functions, there's a shortcut that is provided in the purrr package. You don't have to say function of x, then the body. You can do the following. You can accomplish the same exact thing as the last code chunk with map of twiddles, UNIF, grab 3 things, min is 0, max is dot. And the dot there means that's the argument that is fed into this function that you've just defined. And so the argument will be first 3, then first 1, then 3, and then 5. Check it out. Yep, works the same. So feel free to use that shortcut if you like. I don't particularly enjoy using it a great deal. I tend to write out function of something, then the body. But for these next few examples, I'll just force myself to use it for practice. I'm going to go ahead and clear the global environment again. And let's go ahead and get M111 survey read in from package B CSCR. So it comes in on a promise. And check out the next code chunk. Number NA shall be bound to the result of piping that data frame in as the first argument to map. And the second argument is this function, where the body is, you're going to check on whether or not each little piece of M111 survey is.na or not. And you're going to sum up the places where it is.na. Let's go ahead and run it just to see what happens. So number NA turns out to be a nub. It turns out to be this list of length 12. And here's the structure, which actually shows us quite a bit about what's in that list. So what's happening here is that M111 survey, when it got piped into map said, I'm supposed to be given some, like vector or list, something with pieces that I can iterate through. And so it makes the guess that the pieces you want to iterate through are the columns of M111 survey. The height column, the ideal height column, the sleek column, and so on. So each one of those is getting thrown in as the dot in this anonymous function. And so first of all, we're looking for is.na of height. And that's going to be a bunch of trues and falses. It's going to be true where the height was in A, false otherwise. And so since in the M111 survey, all the heights were actually recorded, there were no NAs, then you're going to have a bunch of falses for this vector here. And when you sum up a vector of falses, then of course you get, sorry, I added, there we go. And when you sum up a bunch of falses, then the falses turn to 0 and the sum will be 0. On the other hand, you may remember that 2 people did not answer the question about their ideal height, and so the is.na on ideal height is a vector that's mostly falses, but it has 2 trues in it, and so the sum was a 2. So very quickly, you get a little function that counts up for you how many NAs are in each of the columns of this data frame. And very conveniently, the list has the same names as the names of the column of the data frame that it was fed. Okay, let's clear the global environment again. So just to reiterate, I'm curious, why am I getting these funny warnings? Because more of a survey map. Let me see, is there an error? Not seeing the error. Ah, there we go. Missing that parentheses. All right. So this idea that the names can come along does not work only when you have a data frame. You can get it to work other times. So like say numbers here is going to be the vector 135. Let's get that in global environment. And the names of numbers, let's set that to be 1, 3, and 5. So now number is a named vector. Now numbers is a named vector. I'll just evaluate it down here in the console and you'll see, sure enough. And if we send that named vector into map, where our .f is to take the RUNIF 3 each time, min is 0, max is in turn 1, 3, and 5, then the result is a list where the elements of the list are named. They inherit the names of the numbers vector. So we've learned about map and we've learned about Pmap. It's also good to know that you can have relatives of the map function that don't return lists. Sometimes your result can take on a form more simple than a list, and in that case, if you want to pick out those simple forms, then you can use map underscore int when the result could be an integer vector, map underscore double when the result can be a double precision vector, map underscore LGL when the result is a vector of trues and falses, and map underscore cur when the result is a vector of strings. So check out the next example here on line 413. Number NA shall be bound to the result of M111 survey piped in as the first argument to map int. And then we've got that same .f function where we are counting up how many non-assigned there are in each column of M111 survey. So we'll go ahead and run this. And look at this. Number NA is not a list. It is a vector of 12 integers. So much simpler and easier to get at the data in than if it had been a list constructed by Map. Here's a little printout of number NA if you don't believe me. And look at that. It brings the names of M111 survey along with it. Here's a quick way to use Map purrr to get the type for each of the columns of M111 survey. And so the height column is a double precision vector. Ideal height is double precision, and so on. Here, M111 survey is being piped into Map logical, and then we're applying the is.factor function to each column. So that's going to be true when the column is a factor variable and false when it's not. And so, for example, where you prefer to sit in a class was a factor variable that had those three values, 1 front, 2 middle, 3 back. So we see true here. Okay, that's enough for this screencast. We'll take a look at walk and its friends in the next of our series. See you soon.